Hello everyone. In this video, I'm going to present our paper called Supporting Cross-Platform Real-Time Collaborative Programming, Architecture, Techniques, and Prototype System. I am Yifan. My co-authors include Zichao Yang, Bowen Zhao, Yiteng Zhang, Jinfeng Jiang, Bowen and Hongfei. It is well known that software development requires effective collaboration among programmers. In general, there are two categories of approaches in supporting collaboration during programming, namely non-real-time collaborative programming and real-time collaborative programming. The former, non-real-time collaborative programming, is a traditional and mature approach that has been widely applied in the industry, which is always based on version control systems such as Git. Programmers edit source code in their private workspaces and manually merge other programs' work. In contrast, real-time collaborative programming supports a group of programmers to view and edit the shared source code at the same time. Changes performed by collaborators are transmitted and merged instantly as the animation shows. During real-time collaborative programming, operation conflicts caused by concurrent editing are resolved automatically, which ensures the consistency of distributed source code. Real-time collaborative programming is beneficial in various scenarios. For example, such novel approach achieves closely coupled collaboration in agile software development, supports distributed peer or party programming, enables remote diagnosis and troubleshooting, and many more. As an emerging approach, real-time collaborative programming has attracted increasing interest from both academia and industry in recent years. However, there exists some problems with the existing real-time collaborative programming environments, and one critical issue is the lack of support for cross-platform collaboration. For example, CodeWithMe supports real-time collaboration with IntelliJ IDEA only. Teletype for Atom provides support for Atom only, and LiveShare supports Visual Studio and Visual Studio Code only. None of these systems really permits programs to freely collaborate in an unconstrained manner using different IDEs. We believe the lack of cross-platform support impedes the application of real-time collaborative programming. Secondly, existing prototypes only support file-level consistency maintenance of the source code, ignoring folder-level conflicts. To achieve rapid local responsiveness in the sense that a user's local editing operation can be applied in the document without noticeable delay, real-time collaborative editing systems have commonly been designed with a replicated architecture. Consequently, one critical issue is to ensure the consistency of the distributed documents. Most of the existing real-time collaborative programming solutions can transform and resolve conflicts between file-level editing operations, namely inserting or deleting a string in a file. However, concurrent folder-level editing operations, namely creating, deleting, and renaming folders or files, may also conflict. For example, suppose there are two collaborators, namely A and B. At one moment, A creates a file and B deletes the whole parent folder concurrently. Their development environment may be inconsistent after the two operations have been propagated and replayed at remote sites. Set B has a file created by A, whereas the whole folder is deleted in set A. The two collaborators' file trees are different now. To address the above-mentioned issue in real-time collaborative programming, we propose, design, and implement a novel cross-platform real-time collaborative programming framework, CP-Roof. Based on CP-Roof, specific collaboration clients on different platforms can be designed and implemented with little effort. In our study, we have implemented two client prototypes based on CP-Roof, which has enabled real-time collaboration over IntelliJ IDEA and Eclipse. I'm going to present our design objectives, workflow and functional design, system architecture and components, major technical issues and solutions, and a set of experimental evaluations in our study. We aim to address the two major limitations of existing real-time collaborative programming environments as presented just now, which means, from user's perspective, our solution should be capable of supporting cross-platform real-time collaboration and unconstrained multi-level consistent maintenance. Collaborators can create, delete, or rename files or folders in the shared project at any time, while others are editing files or folders concurrently. In addition, we also aim to design an extensible and adaptable framework. The proposed framework can be applicable for supporting real-time collaboration with any programming language, and provide interfaces for easily integrating other functionalities, such as collaboration awareness support. To achieve the above-mentioned design objectives, we propose a novel cross-platform real-time collaborative programming framework, CP-Roof, which serves as an essential part of our solution. I'm presenting the design of the generic workflow and functionalities of real-time collaboration based on CP-Roof from an end-user's perspective first. Although different programmers may prefer different IDEs and tools, the collaboration workflow can be unified. Firstly, to initialize a collaboration session, a programmer may choose to create a brand new repository based on local folders and files. When other programmers choose to collaborate with the programmer, they can join the session by the identity. The server transmits the copy of the repository, including all folders and files, to each collaborator in a short time. After collaborators join the same collaboration session, they can start to work in the real-time collaboration style. According to design objective B, collaborators can edit source code files, create new files or folders, and delete any file or folder in the shared repository. The editing operation will then be propagated to all other clients within the session. The conflicts between multi-level operations will be resolved by CP-Roof automatically and transparently. A collaborator may leave from the session at any time, and other collaborators will be notified when a programmer leaves. CP-Roof provides out-of-the-box support for realizing this generic workflow, while specific collaboration clients may provide additional functionalities as appropriate. Based on the workflow and functional design above, we propose and design the cross-platform real-time collaborative programming framework, CP-Roof, as follows. This slide provides an overview of CP-Roof. As a generic cross-platform framework, CP-Roof doesn't capture or apply editing operations from users directly. Instead, specific adapters interact with collaborators and handle operations from users directly based on the common components provided by CP-Roof. We have designed and implemented two specific adapters in Java programs named CoEclipse and CoIdea. They are in the form of plugins on Eclipse and IDEA respectively as illustrated. Editing operations will be processed by CP-Roof after being captured by plugins. CP-Roof consists of three components, namely CP-Roof Core, CP-Roof Client, and CP-Roof Server. Let's dive into more details about these components. According to Design Objective A, the proposed framework should support multi-level collaboration operations in cross-platform real-time collaborative programming. CP-Roof Core provides the model of user-generated operations. The model is language neutral and highly extensible to support more diverse operations when necessary. To provide multi-level consistent maintenance, CP-Roof Core also includes an integrated transformation function for creating, deleting, renaming, and updating operations in both folder level and file level. I will talk more about it later. As for CP-Roof Server, it is responsible for maintaining all files in working sessions and managing all persistent connections with clients. In real-time collaborative programming, collaborators will receive editing operations from others instantly. CP-Roof Server is a central coordinator to receive and broadcast source code files, editing operations, and various notifications. This central document server works not only for notification but also for consistency maintenance. CP-Roof Server serializes editing operations and allocates a total order, which helps ensure correct transformation and execution ordering. As a part of the cross-platform framework, CP-Roof doesn't interact with users directly, but the CP-Roof client supports out-of-the-box design and implementation for various clients to support real-time collaborative programming. Depending on CP-Roof client, specific IDE plugins can support the whole workflow described just now with little effort. Each core from collaboration plugins on different platforms will be transformed into universal formats and transmitted to CP-Roof Server. Remote operations received from CPU server will also be transformed and meticulously and executed in the local environment. That's why we call it the transparent collaboration client adapter. I'd like to emphasize that the communication layer of CPU client is responsible for establishing a connection and exchanging messages with CPU server. WebSocket is used by default and it is sensible to use a different protocol, only if the protocol supports specific means of information interchange defined by CPU. Now, I'd like to present some technical issues and solutions involved in the design and implementation of CPU. Operational transformation is widely used to support consistency maintenance in the replicated architecture. Previous studies have shown one basic strategy to apply OT is to separate the high-level transformation control algorithms from the low-level transformation functions. Control algorithms are responsible for controlling the order, target, and reference of transformation. To reduce the complexity, we have adopted and implemented a high-level control algorithm called context-based operational transformation (COT) in CPU. To combine COT algorithm with cross-platform collaborative programming, we have to consider how to perceive editing operations from users and coordinate local operations and remote operations. Firstly, we have to ensure processors that handle local operations and remote operations compete orderly for the execution of OT module. Secondly, we have to ensure that the context of the editing operation being executed is the same as the state of the document that is being changed. In other words, if another thread changes the document after a transformation and before the execution of the operation, the transformation based on all the context will become invalid, and the execution may modify the document wrongly. Only by ensuring these two conditions can we ensure the consistency between document replicates over collaboration sites. To ensure these conditions, we have designed two strategies to maintain the consistency of document content and the structure of file level respectively. Firstly, when a local file level editing operation is detected by the system, before it is applied in the document, the local operation processor will request a lock in the OT module of CPU client as is illustrated. If there is currently a remote editing operation being transformed and executed, LOP will be blocked until the remote operation processor completes the transformation and the document state is changed. Things become different when it comes to folder-level editing operations. Collaborators may change the local file tree in a mess of ways. It is hard for CPU to detect local editing and request the lock before local operation execution. Therefore, we propose a novel coordination strategy for folder-level editing operation transformation control. As illustrated in this figure, LOP requests the lock when it receives a remote editing operation, but LOP will not try to acquire the lock until it detects the local file tree has been changed. If any remote editing operation is executed in a different file tree state after transformation, a conflict will be perceived. The OT module will try to fetch the updated file tree, transform and execute the remote operation again. In this way, we control the multi-level transformation orderly. In order to integrate file-level and folder-level OT algorithms supporting such transformation control and reduce the complexity of the system, we devise a new set of conflicts and compatible relations between editing operations. These relations help us devise and implement a set of new transformation functions. They are described detailedly in section 5.1 in our paper. I also wish to stress the process of developing a new collaborative programming client with the full use of components provided by CPU. It involves three simple steps. The first one is to identify the mechanism of listening for editing operations on a different platform. Secondly, implement direct editing of local files and folders. The last step is just to invoke the common components from CPU. The purpose is to receive editing events and display collaboration notifications. We have implemented two clients named the co-Eclipse and co-Idea as reference implementations based on the Eclipse and the IntelliJ IDEA platforms respectively. They can support the whole workflow mentioned before. This short animation demonstrates the process of cross-platform real-time collaborative programming based on co-Eclipse and co-Idea. The co-Eclipse and co-Idea prototype implementation have confirmed the feasibility of cross-platform real-time collaborative programming based on the CP-Roof framework. A group of programmers have been invited to participate in our preliminary user evaluations. The picture on the right is taken in our laboratory. 3 programmers are participating in the user evaluation of co-Eclipse and co-Idea. They provided positive feedback on co-Eclipse and co-Idea. In addition to such user evaluations, we have conducted a set of performance evaluations on key procedures critical to user experience. We fetched several repositories from GitHub with diversity in project size. As illustrated in this table, even for large-size projects, the time course for initialization was still acceptable. It can also be observed that the local editing operations are always captured and applied instantly. The duration from an operations generation to its remote replay mainly depends on its transmission over the network. We have also compared these key performance factors among our prototype and the other 2 representative single-platform real-time collaborative programming tools. It demonstrated that the proposed CP-Roof achieves cross-platform collaboration without noticeable time overhead. Moreover, we conducted further experiments to confirm the scalability of CP-Roof in supporting real-time collaboration by a large number of participants. We have designed 2 simulation scenarios. In the first scenario, there is 1 local site and n remote collaborators working in the same session. Each remote site performs an editing operation concurrently. In the second scenario, there is a local site and a remote site working in the same session. It can be observed that even for a large amount of collaborators, the proposed framework can transform multi-level operations with acceptable time costs. To conclude, real-time collaborative programming is an emerging approach that enables a team of programmers to edit shared source code concurrently. Our work has contributed a novel cross-platform real-time collaborative programming framework, which supports real-time collaboration for programmers using different IDEs. Both file-level and photo-level consistency maintenance have been supported and integrated. Following the CP-Roof framework, we have successfully implemented 2 client prototypes named co-Eclipse and co-Idea to support cross-platform real-time collaboration over Eclipse and IntelliJ IDEA. Preliminary user evaluations have confirmed that all design objectives have been met, and performance evaluations have demonstrated the high efficiency of the implemented prototype system. We are continuously working in the domain of real-time collaborative programming environments. We plan to invent more functionalities, improve and validate the proposed local control, and continuously improve co-Eclipse and co-Idea. We invite you to read our paper for more details on the framework. Thank you much for your attention.